Okay, we're continuing with our StressStrain PowerPoint video. This is where we left off. And here we are. This was our proportional limit, and now we're at the elastic limit here. Resilience has to do with the amount of energy per volume that a material can absorb in this elastic linear range. And we can specifically find resistance by finding the area under this part of the curve. For example, in a car bumper, we want to know how resilient it is. How much energy can it resist before it permanently deforms? Right before we start this curve part, that's the yield point. If we go from the yield point down, we find this offset yield strength, often about 0.2%. This section is called the plastic deformation. Be sure you write this on your graph. In this section, if I pull any farther in this section, it's going to get longer and it's not going to go back to its original shape. Think about a plastic water bottle. If you crush a plastic water bottle, it's not going to go back to the same shape. This is called plastic deformation, and this is where failure is. As it gets longer, the cross-sectional area starts to decrease there. You'll see an example in a picture in a second. But it's also getting harder. In this section, that part where it's actually changing shape gets slightly harder. The weakest point is stretched and becomes stronger, and so on. Here you can see where it's getting smaller cross-sectional area there, and that's the part that was getting stronger. When you hit this point right here, it's the maximum stress, and that gives you the maximum tensile strength. Put this on your graph. And we call this section where it gets narrower necking. It'll eventually, if you keep pulling, it'll eventually break, as this example here did. This point right here is the point of failure. Mark that on your graph. Depending on what it looks like, tells us how brittle or ductile the sample is. If it snaps off cleanly, think about like chalk, it's very brittle, like chalk breaking. Something that stretches a lot, like this, is more ductile. We can also see it in the graph itself. If it strains a lot, strain, remember, is elongation, it's ductile. If it breaks with just a little bit of stretching, like, say, chalk would, then that is brittle. Toughness is another thing we can get from this curve. If we calculate the total area under the curve, we find the value for the toughness of that material. We talked about tensile test where we pulled on the materials, but you could also do compression test where you push on the materials. And there's also hardness test. You've often talked about these in science classes like chemistry, where they test how hard something is. That's how much does it resist if you drop like a ball onto the material. Does it leave a dent or does it not? And the Rockwell test also tests for hardness, where they actually use a diamond-tipped cone and push it into the sample and see how far in it goes. And that's the end of part 2.